Hello, ladies and gentlemen, what's up? I hope this video finds you well. In the last video, I discussed how to like derive this limit when x is approaching zero of x raised to the power x. I derived the expression which came down to being equal to one, right? So mathematicians use this as a proof to like justify, rationalize that zero raised to the power zero equals to one. It is not exactly equals to one because zero is still an intermediate value because of certain paradoxes which I discussed in the previous video. Um, I also discussed the reason for any other number raised to the power of zero equaling one, which is essentially just like just for example 0.001 upon 0.00001, right? So the numerator is also raised to power one, denominator is also raised to power one. By the law of indices, the power of denominator just subtracts from the power of the numerator, which is essentially just one, essentially just zero, right? So also like basic mathematics tells you that the numerator and the denominator cancel out in such cases, which is just one, right? So even if I like increase zeros here, I add a couple more zeros, like keeping the zeros in the numerator and the denominator equal, I will get one, right? So as I keep increasing zeros, the expression would still evaluate to one, right? This is the base core reason why mathematicians assume this. Mathematicians assume that this is exactly equal to one because of certain applications where this comes as like efficient and not as tedious as using something else like zero is about zero equals zero. This becomes useful in certain applications. I discussed a couple in the last video. Watch the video if you haven't, right? So these certain paradoxes, I wrote them down just like for a quick showdown here, like just to like make sense of what I'm saying so that I'm not blabbering without any visual input, right? Yeah, so Thomas Calculus also states this one question where you have to like determine a value for an expression that on the first glance, if you put infinity in place of x, like if I say that the limit of x is approaching infinity, like put over this is just infinity, and ln x as x is approaching infinity is simply just infinity, right? So this is zero and this is zero, but this expression does not approach either zero or one. This expression does not approach either of these values, right? You can use this as a proof for the fact that zero is to the power zero is an intermediate value, but a mathematician will tell you that the rates of change vary, right? I have written all of this before. This is me like reviewing what I did a couple minutes ago because my stupid screen recorder didn't record properly. Okay, so I mean, come on, I'm using snipping tool here, all right? Cut me some slack. Okay, so yeah, uh, you can see the graph of y equals to x is just a straight line, and the graph of y equals 1 over x is forms an asymptote with the y-axis, right? It is approaching y-axis at a gradient that is decreasing as you the magnitude of the gradient is decreasing as you're approaching y, right? That is why it's an asymptote, right? But the value of this decrease in gradient, the d square y upon dx square is actually like kind of greater than the that of this, I think. Yeah, wait. Yeah, I do think so. Yeah, it does seem like that. It does seem like that. All right, so I just woke up. I cannot do that mental math right now. You can write it down, or like you can just see the graph at Desmos. But the rates of change of these both graphs approaching the y-axis is different, right? Different rates of both graphs approaching the y-axis, right? So you cannot determine the value of zero is about zero, like foolproof determination of the this value using this formula, right? Using this formula. So a mathematician will tell you that because the rates of change are different, right? But like if we are not going to solve it by limits, right? So we are still going to prove why this expression does not evaluate to zero or one. because this expression does not have anything to do with 0 raised to the power 0. This expression has nothing to do with 0 raised to the power 0. This is just a mathematical tool, right? This is just a mathematical expression. This is just a mathematical, what's it called? What's it called? A mathematical jargon. I would say this is just a mathematical like tomfoolery. We are not going to solve it via limits. Like we are not going to use any limits here. We are just going to solve it like base algebraically and using indices. So I solved it using two different ways here. The way one, I mentioned the way one of solving here, right? The way one is saying that 1 raised to any power is simply 1. That is the base of mathematics, right? You know that since preschool or something, something like that. So I just like brought the power into the fraction, the power because it's like bracketed here. So 1 raised to the power 1 over ln x is essentially just 1 because of this. And x is 1 over ln of x, right? So you get this fraction. And if you remember, ln is just natural log, which has the base e, right? So you can write the 1 in the numerator as ln e, right? So that's what I just did here, 1 over x raised to the power ln e over ln x. And this was another law, another identity for logs, which states the base should be equal in the numerator and the denominator. So the subject in the numerator would become the new base, and the subject in the denominator would still remain the subject in the new expression we derive, right? So using that, you just get 1 over x raised to the power log xe. So log x is essentially just saying what power, listen carefully, all right? Listen to me very carefully, all right? What power of x you need to raise x to. So the value of the value of x raised to that power becomes e, so right? For example, this expression equals to like something like y, right? Y is already in use, so we can say v. So what is the v that you need? So you get the value of x equal to e, right? Equals to the Euler's constant, right? So you are essentially just raising x to that v, and we already know raised to the power v is equals to Euler's constant, right? So just simply using that, you get 1 over e, because 1 over e, right? This expression is e, which equates to something like 0.36, right? So essentially, the expression is just evaluating to this, and mathematicians just like kind of reverse engineered the way here, just reverse engineer. It's just it's just to make like create havoc or something, right? Yeah, mathematicians are stupid. I'm sorry about that if you're a mathematician. Right? Cancel me if you want. uh I shouldn't have said that, I think. Or whatever. All right, so the second way you can solve this is using other identities of logarithm, right? Again, it's just a mathematical, like kind of a mathematician's way to like cause havoc, cause like I am having massive brain fogs right now, right? Forgive me for that. Yeah, so y equals to 1 over x raised to the power 1 upon ln x. So what I did was, this is something you do quite often when you are like when you're solving limits. This is something that you do very often. You just apply logarithms on both sides. When you're solving indices, even this is something like very useful. This is a very handy thing to do when you're working with indices, right? So I applied natural log on both sides, which gives us ln x equals to ln 1 over x raised to the power 1 over ln of x, right? So using the law of logarithms, the power just comes here, multiplies with the natural log. That is an identity of logs, right? So you get ln of y equals to 1 over ln of x multiplied by, so 1 over x is essentially just 1 over x equals to x raised to the power minus 1, right? So I just cut the chase, I cut a couple steps and just wrote this here. Yeah, so the power again just comes outside here, multiplied by here. So you get ln y equals to minus 1. Now there's a negative sign here, over ln of x multiplied by ln of x. The ln of x is cancel out. See here, the mathematicians are just stupid, right? They just say, yeah, I'm gonna make kids suffer. Kids are going to suffer, right? So you just get ln is natural log e ln y equals to minus 1, right? So you just get y equals to e raised to the power minus 1, which is essentially 1 over e. So you get this value back, right? So both ways give the same answer, which is completely free of x. Like it is not determined by the value of x at all, right? This was just a stupid way of like reverse engineering this expression into like this expression to like cause havoc, right? A mathematician would immediately know that this cannot prove that 0 is the power 0 is an intermediate value or not, right? Because the rates of change are different and this expression does not like include x at all. This is just a mathematical notational trick, right? Mathematicians are stupid, right? I hate them, honestly. Yeah, so that I even if you like open Desmos really quickly and like put the expression in here, you just see that the expression is simply 1 over e constant. Like it does not depend on x at all. It is independent of x, right? The value just stays constant throughout. The graph just stays constant throughout. It is not dependent on x, not dependent on x. Right, so yeah, that was what I wanted to discuss. Thomas Calculus mentions this as a reason why you wouldn't want 0 raised to the power 0 equaling 1. It mentions it that way, but I think that is kind of like confusing children simply. But not me. Not me. All right, so yeah, thank you. Bye bye. Thank you. Bye bye. Bye bye. Bye bye. Bye bye. Bye bye.